Welcome to this Tech Talk on fire mitigation using high impedance fault protection. This presentation explores the challenges of detecting high impedance faults, HIFs. We'll explore methods to protect for HIF occurrences. My name is Dan Ransom. I've worked in industrial and utility power systems in protection and communication. I'm from Washington State in the USA, having graduated with a BSEE from Gonzaga University in Spokane, and I have a degree from Washington State University in Pullman. As a senior member of the IEEE, I enjoy working on various standards committees in the associations listed here. I'm a licensed professional engineer in many U.S. states. Our discussion today covers the following topics: the definition and causes of high impedance faults, HIF, the methods for HIF detection. We'll look at a couple of methods and compare those, and then I'll talk about some implementation strategies. First, let's take a look at the definition and causes of high impedance faults. A high impedance fault happens when a primary conductor makes unwanted electrical contact with a tree, a pole, a structure, or with the ground. Because of the large impedance in the fault path, the fault current can be a few milliamps to 100 amps. Even in cases where the instantaneous fault current exceeds standard overcurrent thresholds, the duration of this transient event is so short that the standard fuse or overcurrent elements that we use to detect overcurrent faults, they don't clear or pick up. There is little threat of damage to the power system equipment because these are small currents and are transient. But these events are a safety and a fire hazard. Line crews responding to downed and broken conductor events have seldom documented these on trouble reports. So it's quite challenging to detect HIFs, and it requires special methods combining multiple techniques. So let's explore some of the causes of high impedance faults from downed and broken conductors. So the conductor touches the ground and it might be intact or it might be broken. When the conductor touches the ground or other surface and remains intact feeding a load, we call this a downed conductor. Note there's tension on the wires in the picture. This can be caused by support failure or heavy loading sag. When broken and laying on the ground, we call this a broken conductor. Note that the ends are separated and slack, as is shown in the picture. So weather, nature, and faulty equipment can be a problem. Icing and tree limbs leaning on distribution circuits cause lines to sag and to conduct current intermittently to ground. If a utility does not do an adequate job of clearing vegetation around distribution lines, then tree limbs touch the line irregularly, causing arcing. Contaminated and failing equipment, such as disconnects, fuses, and dirty insulators, can cause arcing and high impedance faults in the distribution system. When we look at the system overall, regular overcurrent elements cover about 90% of distribution faults, including some downed wire events. However, some downed wire events have a large impedance to ground and go undetected. These are the HIFs, and those are shown there in light green. For these high impedance faults, modern relays employ high impedance fault HIF detection to protect people and prevent fires. And the goal is 100% detection of all HIFs, but in reality it's impossible to detect all high impedance faults. However, experience shows that 60 to 85% of HIFs are detectable. So it's possible to achieve a large degree of dependability and security with a reasonably priced detection system. If we assume that 90% of the faults shown in the large blue are low impedance faults or overcurrent faults cleared by fuses and conventional overcurrent protection, and if the remaining 10% of the faults are high impedance down conductor faults, then a modern microprocessor relay with instantaneous time overcurrent protection and HIF detection can operate for approximately 98% of all the faults in a utility system. Note that these high impedance down conductor faults can spark dangerous and costly wildfires, so it's important to provide this protection. When a line is on the ground, it causes an arcing fault. Arcing faults affect the current signature at the relay. The ground path resistance varies during the arcing fault, and the changing current creates nonlinear waveforms. The nonlinearities then produce large harmonic currents. Arcing time for HIF currents is erratic. Usually, these currents decrease over time because the wire-contacted material burns and becomes less conductive. Arcing can stop for minutes, and then it can start back up again. And high impedance faults can persist from seconds to minutes, and sometimes for days. This makes it a challenge to detect and classify these faults. Fault arcing and currents differ on various surfaces, as shown in this table. Without arcing current, high Z detection is unable to declare a down conductor. For example, down conductors on dry asphalt and dry sand cannot be detected because both surfaces do not produce arcing currents. In contrast, reinforced concrete with lots of metal rebar provides the most arcing. Tests indicate that 60 to 85% of all down conductors can be detected. This means that 40 to 15% of all faults cannot be detected because not all surfaces produce arcing current. Ideally, HIF detection should detect all HIFs and should be secure, ignoring normal conditions. Detection should be immune to false positive indications and misoperations. HIF detection must then differentiate between the HIF current signatures and the waveforms from intermittent and noisy loads. Examples of loads that generate power system noise are arc furnaces, welders, capacitor and line switching, load tap changing, DC rectification, motor commutation, and starting. The ideal HIF detection technique can evaluate and subtract these loads from the arcing algorithm. Detecting HIF is vitally important. Arcing from high impedance faults causes fires. Undetected live down conductors can be fatal to the public and to line crews. A line that's arcing results in line failure, which leads to power outages and loss of production, affecting economy and human well-being. And HIFs cost utilities liabilities and service problems. Let's look at some techniques for HIF detection. There has been a traditional broken conductor detection method, an established technique that's been in use for over 20 years. It does not detect arcing. It works on the principle that a broken phase conductor produces unbalanced current. It uses negative sequence current I2 and positive sequence current I1. The relay calculates a ratio of I2 over I1. A limitation of this method is that in very lightly loaded and unloaded feeders, there are large standing unbalanced currents. So typical settings for this method are the following. I2 over I1 greater than 20%. This is to accommodate for the unbalance. There are long delays, approximately 60 seconds, for coordination with phase ground overcurrents. Single relays using this method are insensitive to declaring a down conductor and have had limited success. However, there is some recent technology proving to be very promising. It uses networked phasor measurement units, PMUs, that detect a change in impedance. The PMUs report into a central system-wide monitoring gateway. We call this high-speed falling conductor protection, and it has promising results. I presented this topic in a tech talk earlier this year. So we use modern techniques to analyze arcing. We look at the arcing signature. The red and gray lines in the graphic here are variable arcing current shapes, reference to an ideal sine wave in blue. These methods analyze the arcing time domain and frequency domain aspects. They measure increments in the current inputs, not the absolute and peak values, and these methods incorporate load analysis and pattern recognition. We'll investigate two arcing detection methods that I call Method P and Method F. Method P is in the Agile P14DZ protection relay here on the left. Method F is in the Multilin F60 universal or UR relay shown on the right. Method P employs a core balance or zero sequence CT as indicated here. It detects arcing faults by dividing the analog current input signal from the CBCT into an overall arcing detection portion called fundamental analysis and into a third-fifth harmonics portion called component harmonic analysis. In addition, Method P uses voltage for a sensitive power calculation to determine direction, the DIR algorithm. This method works well for ungrounded and resonance-grounded Peterson coil type systems. Method F has a special HIF analog input module, the 8Z, that amplifies each of the four inputs for three-phase currents and the residual current inputs, as shown here. It's wired in series with the existing relay CT inputs. This 8Z module amplifies phase and residual currents and monitors load on the phase currents. Because the UR line in the F60 is modular, you can add the 8Z HIF module to existing F60 relays. A simple feature update via firmware completes the process. In addition, the Method F HIF processing uses voltage for phase identification and restraint. Now let's dive deeply into each of the methods. First, let's learn about Method P in the Agile P14DZ relay. Method P HIF detection evaluates fault current waveform signatures. These waveforms differ from fault to fault and even within the same fault occurrence. Method P uses fundamental analysis to quantify transient bursting, the random changes of amplitude, with counters and timers. Also in use is component harmonic analysis using third and fifth harmonics, detecting the periodic distortions at the zero crossings. To establish the fault direction, Method P uses an instantaneous power measurement in the directional analysis DIR algorithm. The overall block diagram for Method P shows the sensitive earth fault current input, ISEF, from the core balance CT and the voltage input VN at the upper left. Settings and reset are additional inputs to the Method P HIF function. The two paths to the output are via fundamental analysis, FA, and component harmonic analysis, CHA. For each of the FA and CHA paths, the HIF outputs are transient, arcing detected, and HIF. In addition, the FA path outputs a steady fault operand. The main output is the ANDed combination of the FA HIF and the CHA HIF outputs, called HIF alarm. Fundamental analysis captures the intermittent characteristics of the high impedance fault residual current from the core balance CT. Generally, the system current is stable and tracks the load conditions. So Method P averages the sensitive earth fault current, summing the latest samples and storing this value in a buffer. The relay compares this value continually with the latest current value. If there's a sudden increase in current, then this value significantly exceeds the average value. It is this increment that starts the fault evaluation process. Fundamental analysis is triggered by any sudden increase of the amplitude. The algorithm counts bursts in a time window. Only these sustained series of changes within the time window are evaluated as HIF, as seen in the upper graphic. A transient event has insufficient bursts in the time window. And in the lower graphic, a transient event needs further sections for HIF determination. Component harmonic analysis, CHA, measures the sensitive earth fault SCF current from the core balance CT and compares this with the average current value and uses the increment of the sampled value to extract the third and fifth harmonic components. As seen in the graphic, CHA evaluates the phase and amplitude thresholds and differences between the fundamental and the third and fifth harmonics to determine the presence of HIFs. The satisfied state is the value that indicates HIF nonlinearity. CHA measures the duration of the satisfied state to evaluate and classify faults. The criteria determining HIF nonlinearities are the following. The fundamental amplitude is greater than a set threshold. The amplitude ratio between the third-fifth harmonics and the fundamental is greater than a set threshold and is greater than 90% of the fundamental. The phase difference between the third-fifth harmonics and the fundamental is within a certain range, and these effects last for a significant time. CHA detects a fault by timing the duration of the satisfied state. If this time is longer than the HIF setting, an HIF event is reported. If the duration is shorter, but still longer than a transient setting time, the algorithm reports a CHA transient event. Directional analysis helps with resistance impedance grounded systems. The fundamental analysis algorithm has no capability of detecting a direction. FA only is best used in a system with limited capacitance or a system with a directly grounded neutral point. In these cases, the fault current on healthy lines is limited. However, when a system is resistance grounded, the fault-generated transient might be dispersed along both healthy and faulted lines because of a large distributed capacitance. Therefore, a directional element enhances the FA performance for these systems. The relay uses fault instantaneous power direction to obtain the transient direction, calculated directly from the fault component, the zero sequence samples. In transient situations, this is a more accurate method than using phasor-based power calculations. The fault component circuit is used for analysis. The source is the fault itself. The capacitive branch produces the reactive power, while the inductive branch absorbs the reactive power. The resistance branch absorbs the active power from the source. The reactive power from the source balances the total consumption of the reactive power by the other part of the circuit. Generally, the reactive power is more distinctive because the distributed capacitance is greater than the distributed conductance. The table shows that in resistance-grounded and in isolated systems, the reactive power direction is used for transient direction detection on the faulted lines. In Peterson coil-grounded systems, the active power direction detects the direction because the Peterson coil cancels reactive power flow. When counting a spike into the FA functions counter, the FA first refers to the direction flag. Only spikes with the forward direction are counted for fault evaluation. So here are some method P recommendations. Select the HIF solution according to the system grounding. FA detects intermittent faults where the fault current is changing between conducting and non-conducting. This can be used in any system grounding conditions. CHA detects situations where there is a regular earth fault harmonic. CHA should only be used for directly grounded and for low resistance grounded systems. As noted here in this chart, the directional element helps with Peterson coil and isolated systems. So method P HIF detection field trials were performed on a 13.8 kV feeder with a resistance grounded source. A 50-to-1 core balance CT fed the protection relay. Here are some waveforms recorded from these down conductor tests. These waveforms show the erratic signature of arcing in rocky sand. Note the transition from FA transient to FA HIF marked in this graphic. When we zoom in on the rocky sand waveform, we can see the FA increment increasing, causing burst detection. The component harmonic analysis CHA algorithm produces an HIF output for this arcing. The third harmonic ratio increases and the phase difference shifts. The CHA algorithm detects. A line dropped on asphalt exhibited residual current too small to activate method P. Now let's learn about method F in the multilin UR F60 relay. 9 sophisticated algorithms make up the method F HIF detection. High impedance fault detection is accomplished through a variety of techniques, and these are all coordinated by an internal expert system. The HIF protection system monitors and learns the power system nominal behavior. At the heart of the HIF detection system is identification of arcing on a feeder. If arcing is detected, the expert arc detector determines whether the arcing persists for a significant period. If it does, it analyzes load current. This is to determine whether persistent arcing is from a down conductor or from an intact conductor. There's a collection of sensitivity and timing settings that tune dependability and security. The method F outputs are the following shown here. Arcing suspected, which is intermittent arcing with no load changes. However, there's lots of expert arc detector counts. Arcing alarm, this is arcing without loss of load or overcurrent condition that indicates a bad insulator or a tree or other object on an intact conductor. Lots of expert arc detector counts, EAD counts, in the time window occur with this alarm. A down conductor, this is arcing initiated by loss of load or overcurrent when the conductor breaks. And there's a phase identification output, which is the phase of the downed conductor. To accomplish this, the method F algorithm has many parts. In the HIF element, we determine that a down conductor exists. There are oscillography and fault data captured. In addition, target messages and appropriate LEDs activate on the relay faceplate. So to detect a down conductor or arcing condition, we use these following algorithms in the F60. Energy algorithm, randomness algorithm, the expert arc detector, the load event detector, the load analysis algorithm, the load extraction algorithm. We take a look at arc burst pattern analysis, spectral analysis, arcing suspected identifier. There's an even harmonic restraint and voltage supervision. This simplified block diagram shows signal processing and on through to the energy and randomness algorithms, then to the expert arc detector. Next, the method analyzes overcurrent and load loss to output arcing alarm, and if arcing is not prevailing, to the arcing suspected output. Further restraint and voltage supervision secures the down conductor output. Here we see a more in-depth look at the operation of the HIF detection. The relay processes phase and neutral current inputs for 60 Hz and odd, even, and non or inter harmonics. Voltage inputs have a confirmation check. The relay processes load extraction, arc burst pattern, and spectral analysis. The results of these analyses proceed to the energy, randomness, and pattern analysis algorithms. Next, the expert arc detector decision structure provides separate HIF outputs for arcing suspected, arcing alarm, down conductor conditions, and phase identification. It's important to avoid nuisance outputs. Method F avoids nuisance outputs using many strategies. HIF detection monitors RMS currents, not instantaneous values that could false the HIF algorithms. Measured increments track bursts over time, not absolute values. This HIF method adapts to changing conditions and loads. Upon power-up, method F learns the feeder ambient harmonic energy level. It determines an ambient average noise level for the odd, even, and non-harmonic energy components of the currents each hour for 3 days. Then it takes the worst average value over this period and uses it as the harmonic noise threshold. The HIF algorithms ignore any harmonic energy patterns in the current below this ambient level. If the harmonic energy on the feeder changes, method F redetermines a new ambient level to adapt to changing conditions. Another method for avoiding nuisance outputs is to use even harmonic restraint and voltage supervision as final tests before declaring a down conductor. Here's an example of method F declaring a down conductor. These oscillograms are available to you to determine the functioning of the HIF algorithm outputs. Here we see a sudden loss of load or an overcurrent condition that starts the overcurrent coordination time. Once this timer here, 10 seconds, expires, there are sufficient expert arc detector counts greater than the arc confidence threshold level to declare a down conductor on phase A. In some cases, arcing is present, but it's not persistent. For example, when it's caused by a tree limb contact or an insulator degradation. Arcing typically is present intermittently, interspersed with relatively long periods of inactivity, such as minutes. In these cases, arcing can be affected by factors such as the motion of a tree limb or the moisture and contamination on an insulator. Conditions such as these, characterized by many brief occurrences of arcing over an extended period, for example from a fraction of an hour to 1 or 2 hours, lead the HIF element to recognize and flag an arcing suspected event. None of these brief occurrences of arcing, if taken separately, are sufficient to indicate the detection of a down conductor or to set off an alarm indicating that persistent arcing has been detected. However, when considered cumulatively, these do indicate a need for attention. So if an output contact is configured to indicate arcing suspected, the HIF element recognition of this periodic arcing closes that contact and appropriate investigation can be taken. Let's summarize method F, high impedance fault detection, in the F60. Arcing causes bursts of energy to register throughout the frequency spectrum of the currents. These arcing bursts have distinct qualities and signatures. Several of the HIF algorithms detect these patterns. The odd, even, and non-harmonic components of the phase and neutral currents are analyzed for these distinct patterns. The algorithms look for energy and randomness patterns and learns and removes normal load noise effects. Separate outputs of the arc detection algorithms feed into the expert arc detector. The basis for down conductor detection is event dependent. Differentiation between an intermittent arcing intact conductor and an arcing down conductor is determined by looking at the patterns in the load current at the beginning of the fault. User settings determine what constitutes a loss of load or an overcurrent condition. When a conductor breaks, generally there is a loss of load or an overcurrent condition when a phase hits another phase. This gives an indication that the conductor broke. The detection method looks for arcing to determine whether the conductor has fallen to the ground or hit a grounded object. A down conductor is only when a loss of load or an overcurrent condition precedes arcing detection. If there is only arcing and no loss of load or an overcurrent condition preceding the arcing detection, an arcing alarm is issued. It's not a down conductor output. It's assumed that the line is intact with arcing present. This might be a bad insulator or a tree rubbing an intact conductor. If the detected arcing is persistent, an output contact closes. Next, I'm going to present some details of the F60 HIF system installed in a major distribution utility. Pepco Holdings Exelon provides power to 2.3 million customers in the Washington, D.C. area and parts of Maryland. The service territory covers approximately 640 square miles. The distribution system has 1,500 13 kV feeders. Half of the feeders are overhead 4-wire, multi-grounded, and this is a good example then for assessing HIF performance. Many utilities have performed their own staged fault tests on both grounded and ungrounded distribution systems. These drop tests are where a line is dropped intentionally to test the operation of the detector. Shown here are photos from Pepco's initial line drop testing, where the HIF method F relay, the F60, detected 82% of down conductors. Later on, there was an extensive study done with HIF detection. So Pepco conducted a 17-month study on the efficiency of the HIF technology. They operate the system with tripping versus alarming, and we'll discuss that more later. The down conductor declaration therefore trips the associated feeder. Operation occurs only if an HIF is truly present, which can be either detection of both intact arcing and broken down conductors. Pepco operates with a delay to wait for the conventional overcurrent to operate. In this manner, the conventional fuse saving and fuse sacrificing schemes can operate. The overall purpose of the study was to examine the records to enhance the safety of the public and employees and to minimize property damage and fire. The criterion included proof, so the event must have an indication from the operator log or from a relay target, and the relay data and oscillography support analysis and the conclusions. So the experience study involved 780 relays during 17 months, which is 1,105 relay years. This sample size is sufficient for determining valid results. There were 3 operation classifications in the study. These are successful operation, where the relay tripped, declaring a down conductor, and the operator log mentions a wire on the ground. Another classification is non-down conductor HIF operation, where the relay tripped on a down conductor, but there was no wire on the ground. Only arcing symptoms were found. So this case is an arcing alarm and arcing suspected. And the third classification was unsuccessful operation, where the relay tripped for down conductor and the operator log does not show evidence and there was no HIF detection found. Here are the study results. PEPCO recorded 42 down conductor events. Of these, the successful result was 29 operations, or 70%. The correct non-down conductor HIF operations were 6, or 13%. And unsuccessful operations were 7, or 17%. So the overall success and correct operation of the HIF detection system was 70% plus 13%, or 83% HIF detection. Let's take a look at some HIF detection examples in this study. First, here are the phasor waveforms from a successful down conductor HIF operation. Note that the current in phase A is larger. There are lots of harmonics in this waveform. Phase A shows a loss of load. So the current in the healthy phases is steady. There are very few harmonics, and the voltages at the bottom show no distortion. Here we see the high Z oscillography taken from the F60 relay. Note that the accumulated confidence in phase A rises rapidly because of the large and varying harmonics. The arcing detected alarm asserts 3 times. Then the relay declared down conductor when the high Z element triggered after the loss of load ALOL flag. Investigation by the PEPCO crew actually did find downed wires. Next, here's an example of a non-down conductor HIF operation. The phasor waveforms show that all phases have large harmonics. This event was during stormy weather, which caused much switching and system disturbances. Also note that phase C current shows a repeated glitch. Here we see the associated high Z oscillography. In this operation, the 3-phase IOC arms down conductor. Then, when there is no high Z signature in the next 70 seconds, suddenly a high Z signature appears, and sufficient confidence builds in 18 seconds. So the relay then declares a down conductor. Originally, this operation was classified as false. However, the crew went out and found a tree limb hanging on phase C. So the relay issued arcing alarms before declaring the down conductor. This is an example of an unsuccessful HIF operation. Note that the phase currents are unbalanced and there are 2 simultaneous dips in the phase B and in the neutral that last 250 milliseconds. Examining the event records, we see that the event sequence over 3.5 hours shows the following. The high Z loss of load B operand picked up many times. Next, the high Z arc detected. And finally, the relay asserted the high Z downed conductor B operand. Analysis of these events indicated that it was likely a VFD, a variable frequency drive or inverter malfunction in phase B. In this example, extraordinary conditions satisfied the relay HIF algorithms for loss of load and energy and randomness. A crew dispatched to the feeder found no down conductor. The study showed that the PEPCO system achieved an 83% HIF detection rate, and we must remember that downed wire detection is inherently challenging. There's no present technology that can achieve 100% dependability, And this is because HIFs are variable, unpredictable, and occurrences depend on many factors such as surface characteristics, system grounding, weather, etc. And these challenges call for a balance of safety and reliability in tuning the settings. Experience with the high impedance fault detection method has identified enhancements in the F60 HIF firmware in version 8.3 and later. These are reducing the coordination timeout minimum setting from 10 seconds to 1 second for faster operation, and this is good for wildfire prevention. We've introduced adaptive arming time for the high Z element. The element is disarmed automatically if arcing activity is not detected within 15 seconds. The neutral channel declares only arcing suspected. As per normal, the phase channels can declare down conductor, arcing detected, and arc suspected. There's an improvement in the loss of load supervision. We use voltage supervision to detect that voltages are normal. HIFs don't cause voltage dips. There's an added voltage check so that the voltage in each phase must be greater than 0.8 per unit to assert loss of load. The algorithm monitors circuit breaker status in the trip reclose cycle to prevent using false IOC or LOL events to arm the high Z element. Thus, a fault that opens a circuit breaker disarms a possible down conductor. And there is now a block setting to customize HIF protection. As with all good tools, knowing the tool and applying the tool correctly to your power system requires good engineering. Here are some points to consider when using HIF protection. When determining how to apply HIF detection for arcing and down conductors, consider the trade-offs involved. Unlike most forms of relay protection, down conductor protection is employed primarily for safety and fire prevention. High impedance faults rarely cause distribution equipment damage. In determining whether to employ HIF detection, you should review the circuit to determine whether conventional protection is adequate. Apply HIF tripping, alarming, depending upon experience with the soil conditions and the underbrush growth, the type of the circuit construction, your experience with energized down conductors, and the nature of the circuit load. Recent experience with power line caused wildfires in windy conditions shows that settings groups with faster response in windy weather are a good idea. One popular application is sectionalizing the distribution system when an arc occurs. Upon detecting serious arcing or a down conductor, the closest recloser controller senses the arc and disconnects the line before a fire can start. This is a one-shot trip and lockout sequence. Let's consider alarming and/or tripping for HIF events. It's not practical or advisable to trip the circuit quickly. Some delay is appropriate for power continuity. However, tripping decreases the danger to human and animal life and prevents wildfires and damage to property. In addition, tripping sooner limits legal liability and litigation, especially during wildfire conditions. Under non-wildfire conditions, consider alarming for arcing faults and keeping power continuity. Send a crew immediately to investigate. Sectionalized tripping relieves the impact on supply continuity as well. And as stated previously, the small currents in arcing faults are a small risk for power system asset damage. So depending upon your experience with soil conditions and the line build-out, you can evaluate the likelihood of unwanted trips. Replace fuses with HIF detection equipped relays to manage distribution arcing protection, especially at the ends of lines. I mentioned earlier that there is a high-speed falling conductor application that detects a line break and disconnects the conductor before it touches the ground. Combining this application with HIF arcing detection gives enhanced wildfire prevention. There's a series of events that occur when a conductor breaks. Shown here at the yellow star is the line break after a period of normal service. It's at this time that high-speed falling conductor protection, HFCP, operates. Operation time is less than 500 milliseconds. Once the conductor is on the ground, the fault becomes an arcing high-impedance fault. Arcing fault down conductor detection that we've been discussing in this Tech Talk takes over to improve safety and reduce wildfire ignition. The goal of broken falling conductor protection is to trip the line before it becomes a downed conductor. We call this high-speed falling conductor protection HFCP. The highlights of this method are that it uses multiple inputs throughout the power system, and it's scalable to multiple relays per line and feeder. It's impedance-based. It uses voltage and current measurements. Taking a closer look at the architecture, we see that the grid node HFCP is a substation solution. We have PMUs installed at selected locations along the feeder. In addition, there is a PMU at the substation. The PMUs at each location operate independently. We have coordination implemented between the substation PMU and the downstream feeder PMUs. There's an IP-based communication between the PMUs and the substation PMU over fiber, radio, and/or cellular. The hardware at the substation is the GE Power Gateway, the GPG, with built-in PMU and firmware for decision-making. Each GPG covers multiple distribution feeders. There can be 50 PMUs for each GPG. The maximum number of PMUs in a downstream chain is 3. PMUs downstream from each other require time coordination, and each one adds 300 milliseconds to the operating time of HFCP, so we avoid having too many PMUs at the same path. The RTC is a high-performance computing platform that supports the real-time control engine and high-speed Ethernet communications with multiple protocols, such as DNP3, C37.118, and IEC 61850. Note that the PMUs can be F60 relays with the high impedance fault algorithm running, as well as the grid node HFCP architecture PMU. Therefore, we can combine the HFCP and the high-Z HIF applications to enhance the likelihood of preventing wildfire ignition. If the falling conductor method does not operate and an energized line touches the line undergrowth, then HIF detects the arcing produced by the down conductor, and it operates as a backup to de-energize the line and prevent the fire. Another advantage of combining both applications is that the high impedance detection notifies you of needed line maintenance when you have an arcing insulator. Usually, arcing precedes a line break. Maintenance crews can then repair the line before it becomes a problem. In conclusion, we learned that HIF protection prevents fires and increases safety. Special techniques are required to detect high impedance faults. HIF methods identify significant percentages of high-Z faults. Modern methods are from 80 to 85%. And applying HIF protection takes some finesse. Testing and experience improves application effectiveness. Now it's time for questions. I've got some great questions that came in during the presentation, so get to work answering these. Here's one. Is fire mitigation protection different from arc flash protection? What type of protection relay use? Yes, fire mitigation on the distribution and transmission line is very different from arc flash protection, and yet there are some similarities. Arc flash protection is mainly for switchgear cubicles. You see this especially in industrial applications, and you see it in utility applications as well. It's to protect operators from, for example, a circuit breaker blowing up. Some of the things that fire mitigation HIF, high impedance fault protection, and arc flash protection share in common is that both of these methods use arc detection methods, with the arc flash protection employing light sensor, some kind of fiber optic, either a point or loop sensor, supervised by excessive current. So you need a hardware or a relay with light sensing in, like the 8 Series 850 or the multi-link Series 350. Whereas on the other hand, high impedance fault protection is similar in that the relays sense arcing with, in this case, special current analysis measure, HIF.
in both the method B and the we discussed these, and then similarity is that these are supervised with an overcurrent event to declare the down conductor. Also in the method F, HIF, F60, there's a special scenario for loss of load supervising the arcing detection. So if you have a large buildup of arcing confidence and then a loss of load, it declares a down conductor. Similarly, the expert arc detector in the FFC method F, HIF, with enough arcing confidence and a short circuit, which could happen when a conductor hits something on the way to the ground or hits something on the ground, it will declare a down conductor in that situation. Here's another question. Can this protection be implemented by negative sequence current detection or broken conductor detection, broken conductor protection? Well, that before HIF was kind of the way we did it. Negative sequence current detection is I2, I1 method that I discussed in the presentation. It's a traditional method to detect a broken conductor. It measures the ratio of the negative sequence current I2 to the positive current I1, as I stated. It works because a broken phase conductor produces an unbalanced current in the system. An advantage of the method is that it's readily available in modern protection relay because it works on sequence components, negative sequence versus positive. So it's available to you where the CTs are applied in the power system. However, unlikely that current in the other phases is going to drop to 0, so the I2 over I1 ratio is valid only for 2-terminal transmission lines. For 3-terminal lines and other distribution lines, then which are generally radial, the effect of I2 over I1 gets influenced by other things like the network impedance, the pre-fault load for low, the break location, presence of distributed energy sources, PRs, inverter-based reading. The high Z arcing methods can overcome these problems and work situations. However, in the I2, I1 method, the unbalance from line loading greatly affects its sensitivity. Normally we set it for 20% or 0.2 per unit, but studies show that it takes a lot of load loss to work. And then, as I pointed out in the presentation, the delay can be tens of seconds to minutes so that you can coordinate phase ground protection. As I stated at the end of the presentation, I talked about high-speed falling conductor protection. If you employ HIZ with HFCP, so you've got falling and fallen conductor protection, then you've got a good chance of catching that situation. You have a robust wildfire prevention. What kind of testing tools are good for high impedance fault detection? That's a good question. Testing it, you go out and commission it, you want to see if it works. You got to prove to the boss that it works. We use ComTrade file playback. So I use a set of test files or I use a test set and play a set of ComTrade test files that I have both simulated ones and actual recording, and it's helped me commissioning confirm that the element set up and set correctly. You can contact me or your local technical application engineer files. Be sure you have a set that plays back ComTrade. Settings, yes, relays are settings. Protection is setting. So what minimum current and time settings are recommended for high Z? Well, the settings for high impedance fault detection help you tune it for dependability or security. Lean to one aspect or the other. I mentioned that in the presentation. It depends on the application. So if you're concerned about wildfire prevention, best to adjust the settings for more operations except some possible false alarm tripping. Better to be safe than sorry, or you're going to operate. And as I discussed, I recommended making the settings more sensitive during weather and seasons that are more wildfire prone, for example, summer. Both the method F and the method P have arcing level and time window settings. Method F, multi-limit 60, among the settings that you can fine-tune, and you can tune method P as well as the arcing sensitivity. And this establishes the belief in arcing confidence, at which the element recognizes arcing and the number of times the algorithm must confirm its belief in arcing before it produces an output. The range in the F60 is 1 to 10 and is the most sensitive. For setting a system that's well behaved, 5 to 7 is suggested range. Then you can monitor the high Z element behavior and adjust it. Other settings that we've got are the phase event count and the ground event count. Those occur in a time window. The high Z settings coordinate with the regular overcurrent protection. You can set the time to wait for this protection to operate from 1 to 200 seconds. Usually I set this small, especially for wildfires, down to the new minimum of 1 second. Change that in Firmware. Or 10 seconds was the previous minimum. Set it right down in there for wildfire protection. We want to be sure we catch those. Also, there is a set of settings for what are the phase and neutral overcurrent minimum pickup. So this is the level at which the high Z element considers a current to be a regular phase current and or neutral current and lets those elements operate instead of arc detection. I usually leave those at the default of 1.5 per unit per phase and 1.0 per. You want these to be greater than the maximum load current for phase overcurrent, greater than the maximum free I0 residual current for unbalanced loading or neutral. Rate of change is something that the F60 high Z element can do. So arcing has a small rate of change of current. Extremely large rate of change of current indicates circuit breaker closing, causing an associated inrush. The inrush currents produce substantial variations in harmonics by the high impedance algorithm, so we want to ignore those. So we've got a setting that we determine what of which rate of change is that we're going to ignore. And I usually leave those at the default. Another type of inrush event you'll see in a power system is energizing a transformer. F60 high Z element has an even harmonic restraint. You can also apply that in the P14P as a logic situation. So when you energize a transformer, there's a lot of even harmonics, a lot of second harmonics. Algorithms evaluate the phase current, percentage of the phase RMS. Then it inhibits the overcurrent flags. Overcurrent is simply caused by transformer inrush or a cold load pickup or something. And just as we can tune the overcurrent and rate of change, the high Z element has a setting to determine what is a loss of load. So that's one of the conditions that supervises the down conductor output. The loss of load flag is set. I saw that in one of the Pepco examples. If high Z algorithms detect a percentage drop in phase current that equals or exceeds the loss of load threshold. The amount of phase current that must increase is based on the setting times the recent average phase current level. That range is 5 to 100%, 5% being the most. Another setting that makes the element secure is to ignore a three-phase fault. Establishes a level at which the high Z element characterizes a sudden three-phase current increase as a three-phase fault. You want to ignore that fault. The last setting I'm going to discuss here is about how you can use voltage to block the loss of load. Low voltage on the feeder can happen when an adjacent has a fault and drops the line voltage. So there's a block setting. Question is how far it is practical to use arc fault detection techniques, on what voltage level. Well, high Z fault detection works on all distribution voltage levels. It's a current analysis method where the relay evaluates the harmonics and randomness of the arcing current. I've done some testing recently in a 22 kV system with a multi-lin F6. Found that the sensitivity there is better when using smaller CT ratios. A Z detection can work at 1200 to 5 CT ratios on all. But when using 600 to 5 and 300 to 5 ratios, the signals are much larger, so the sensitivity setting can be reduced. Question is, what is the cost of HIF protection? Well, the cost of implementing it is small. In both the method P and method F relays, the hardware relay cost is in line with regular protection prices. Note that you need one for each feeder. Already you install feeder protection, so in the case of the F60, you simply add the 8Z module, or 8Z module, which is around $2. On top of the hardware cost, you also need to consider the cost of engineering, settings, and commissioning. Even then, this is a very small amount compared to the damage and cost caused by a wildfire. Well, that looks like about all the time we have for questions. I'm glad to answer any questions online. If you email me, I'm happy to correspond and help you with this application. Definitely want to be sensitive about public safety, wildfires, and deploying HIF, good method I wish to do. Pauline, back to you.
Well, thanks, Dan, and thank you everyone for attending. Please take a moment to fill out the survey at the end and let us know what you thought of today's presentation. We look forward to seeing you again at our next Tech Talk. This concludes today's webinar. Have a wonderful day.